So this is joint work with Barna Saha, and I will speak about Sublinear-Time algorithms for computing and embedding gap at a distance. The added distance is defined as the minimum number of character deletions, insertions, and substitutions needed to transform one string into another. Here you can see two strings at x and y at the distance 3, and an optimum alignment involving one deletion, one substitution, and one insertion. Along with Hamming distance, Hamming distance is one of the two most fundamental string similarity measures, and it is the more robust of the two. Given its wide applicability, there is a wide body of research on added distance. In particular, the classic quadratic time algorithm computing this measure was rediscovered several times in the 60s and 70s. However, since then, the only improvement in the worst case running time came in 1980 when two log factors were shaved off this quadratic running time. And only recently, the birth of fine-grained complexity allowed us to explain this lack of progress. Namely, no truly subquadratic time algorithm is likely to exist. That's because such an algorithm would violate the strong exponential time hypothesis. And this motivated the study of subquadratic time approximation algorithms. Here I state a few milestone results in this lively line of research. In particular, the currently state-of-the-art approximation ratio achievable in truly subquadratic time is 3 plus epsilon, whereas the fastest constant factor approximation algorithm essentially works in nearly linear time, and it was presented at FOCS yesterday. The focus of this work, though, is on sublinear time algorithms, where already linear time is considered to be too slow. And since algorithm breaking this natural barrier cannot read the whole input, we need to specify the model a little bit more carefully. And if the inputs are strings, the standard way to access them is through a constant time oracle providing random access to individual characters of the input strings. We also allow Monte Carlo randomization because both deterministic and Las Vegas randomized algorithms are typically much too weak in the sublinear time regime. The particular variant of added distance studied in sublinear time setting is the decision approximate version of the problem, where the algorithm, apart from the two strings x and y, is also given two threshold parameters, k and k prime. And the algorithm must return yes if the added distance between x and y does not exceed k, and the algorithm must return no if the added distance is strictly larger than k prime. If the added distance is between the two thresholds, both answers, yes and no, are allowed and considered correct. And here you can see running times of the previous and our results for the gap added distance problem. Note that these running times are stated as functions of n and the two parameters k and k prime. The baseline solution is the exact algorithm of Landau and Vyshkin. Note that it's never sublinear time, but it supports k prime even being equal to k, so that's why it's an exact algorithm. The first solution to get sublinear time for some range of parameters is by Batu and others. And this algorithm is actually very fast, but it's also very restrictive in the allowed parameters, namely k prime needs to be linear in n. This assumption was lifted by Andoni and Onak, who at the cost of slightly larger running time. And this running time is still sublinear when k prime is quite large. So in particular, k prime must be much larger than square root n for this algorithm to achieve sublinear running time. The other end of the spectrum was tackled at last FOCS by Goldenberg, Krautgammer, and Saha, who provided an algorithm with running time nk over k prime plus k cubed, ignoring polylogarithmic factors, and this is very efficient for small values of k. And in this work, we improve upon the last algorithm, and our running time is strictly better for medium values of the threshold parameters. But given that all those running times are quite complicated function of n, k, and k prime, let me focus on a specific case when k prime is equal to k squared. This is also known as the quadratic gap added distance problem. And I will plot the running time on a log scale plot with k on the horizontal axis and the running time on the vertical axis. And here, please note that such a plot cannot show any sub-polynomial time factors in the running time. So the baseline solution of Landau and Vyshkin takes linear time, and that's because the quadratic gap added distance problem only makes sense when k does not exceed square root n, otherwise it becomes trivial. Then the algorithm of Batu and others is indeed very fast. It costs roughly 4 foot of n for the quadratic gap added distance problem, but it only allows k to be a constant factor away from the upper bound of square root n. Then Andoni and Onak managed to get sublinear running time for a wider range of parameters for k between the cube root of n and the square root of n. And the running time of Goldenberg and others simplifies to n over k plus k cubed, ignoring polylogarithmic factors, and it is sublinear for k between roughly constant and roughly the cube root of n. Thus, prior to our work, we had two regions with no sublinear time algorithms: around the constant, where this is actually expected due to some lower bounds, and in the vicinity of the cube root of n. And the latter region was undesirable, and that's why the FOCS paper poses an open question to achieve sublinear running time also in the vicinity of the cube root of n. And our algorithm succeeds in that. In particular, its running time simplifies to n over k plus k squared for the quadratic gap at a distance problem, and it provides an improvement for k ranging from the fourth root of n to n to the 2 over 5. This is for the k prime equal to k squared, and the situation looks similar for other values of k prime, as you can see illustrated here for k prime equal to k to the 1.5. Again, we achieve improvements for intermediate values of the parameters thresholds. In this short talk, I don't have much time to cover our algorithm. I'll just say that just like the FOCS 19 paper, we start from the exact algorithm of Landau and Vyshkin, but our relaxation allowed by approximation is even further, even more far-reaching. That's why we achieve fewer DP states, and in consequence, our running time is better. We also get a slightly simpler high-level structure of computations, and in particular, our algorithm is very simple. When k prime is at least k squared, then it has a kind of greedy flavor. In terms of low-level implementation, we reuse, but also significantly generalize the ideas between the low-level subroutines of the previous work. And a much more detailed outline of our algorithm, along with how it builds up on these previous works, is in the long video about this talk, so please check that out later on. In the remaining 2 minutes, I want to cover the extra results we have in the paper. We have 2 of them. So first of all, we have sublinear time algorithms for the same problem, but under an assumption that the input strings are non-repetitive. The only previous work in this area is for the very restrictive assumption in the Ulam distance regime. And then you assume that no symbol can occur twice in a single string. So whenever there's a character A in X, there is only one occurrence of A in the whole X. And there can be another one in Y, but not in X. And in this regime, due to this restrictive assumption, you can achieve quite a lot in sublinear time, namely distinguishing between at the distance k and already 1 plus epsilon k is possible. The running time is roughly n over k plus square root n, and this running time is known to be tight, ignoring polylogarithmic factors and the dependency on epsilon as it decreases towards 0. In our work, we work under a much weaker assumption that for a parameter L specified by the user, there is no length L substring with period 2k or less. And here we can still distinguish between at the distance k and 1 plus epsilon k, and the running time is n over epsilon squared k plus k squared L. And as you can see, when k and L are both small, the first term dominates, and our running time matches the lower bound for the more restrictive Ulam distance regime. The second result is the sublinear time embedding from edit to Hamming distance. Such an embedding in general can be thought as a function mapping string to strings, so that the Hamming distance of the embedded strings can be bounded in terms of the edit distance of the original strings. And the motivation behind designing such embeddings in general is to reduce some computations from the much less understood edit distance world to a better understood Hamming distance setting. And one celebrated embedding is now known as the CGK embedding, which is a randomized function evaluable in linear time. And in terms of the distances, it guarantees up to constant factor contraction and up to quadratic expansion of the distance with good probability. And in our work, we adapt this CGK embedding to the sublinear time regime. And for any parameter p, we can achieve a speed up by a factor p. So we achieve sublinear time of n over p at the cost of a factor p increase in the contraction rate. So now our distances can be smaller, but there is no penalty in terms of expansion or in terms of success probability. So these are the 2 extra results. We call that the main one is our sublinear time algorithm for the gap at the distance problem. its running time is visible on the screen. It's quite complicated, but for the quadratic gap at the distance setting, it simplifies to n over k plus k squared, ignoring polylogarithmic factors. And despite our work, there is still quite a large gap between known upper and lower bounds. In particular, for the small values of k and k prime, the gap is essentially a factor k gap there. So the natural open question is whether this gap can be made smaller. It's not even clear which direction should one tackle, perhaps the lower bound, but maybe the upper bound as well. And the gap is even bigger for intermediate values of k and k prime. That's because our running time has those additive terms, k squared and the third one. And here you can see some two particular cases which could serve as a testbed for designing future Sublinear-Time algorithms. And this brings me to the end of the presentation. Thank you very much for the attention, and I'll be happy to take some questions.
Okay, thank you. So I'll start with one. So you had a graph of the performance in this log axes. So I was just going to ask, what do you think the right answer is, and what kind of lower bounds are there or should there be?
So if you look at this picture, it's very tempting to see that this hump is kind of undesirable. So it would be really nice to draw a straight line all the way from one here to this point. However, if you look at this algorithm, this gives us hope that maybe we can actually even draw a line between this running time and linear running time for the constant values of k. However, the only lower bound we have is just n over k prime. And in this case, this would be a straight line joining this point here and 0, and the value 0 and at half. So the lower bound is here. I can even draw it, I guess. So the lower bound is roughly something like this. And this generalizes to other values of k prime, obviously.
Any other questions? Okay, I'll ask one more. So what are the main structural barriers to improving your results?
So the main barrier is that we have this k squared term. And that's because we kind of are based on the Landau-Wishkin algorithm. And this Landau-Wishkin algorithm has this k squared term in the running time. So this corresponds to the fact that we actually, in a sense, we make k squared so-called longest common extension queries. So we investigate k various shifts between x and y. So you could start at shift 0 when you align xi and yi, but the shift can vary by plus minus k. And then for each shift, we kind of see what happens when at the distance is 0, and then what happens when the distance is 1, and so on. And that's why the algorithm makes k squared such kind of queries. And although we are able to relax these queries so they don't, so that they start at the same position, they don't need to read the character by character, they just can sample characters, but still we make those k squared queries, and that's currently the bottleneck.
Okay, great. So thank you.
Thank you very much.
Yeah. And okay, so I guess our next talk is just about to begin. Okay, so Jonathan talking about testing linear invariant properties.
Great. Can you all hear me and see the slides?
Yes.
Awesome. Okay. Thanks everyone for being here. I'm going to tell you about some recent work I've been doing in the field of arithmetic property testing. This work is all joint with Yufei Zhao, also of MIT. So I'm going to start with a motivating example, a very classical problem in arithmetic property testing that motivates the field. So you're given a function f from a finite field vector space Fpn to the base field Fp. And you want to determine, is this function linear or is it epsilon far from linear? Here, epsilon far from linear means the function's not linear, and you can't make it linear even if you're allowed to change its value on up to an epsilon fraction of the domain, that is on up to epsilon p to the n point. So there's a very classical algorithm which solves this problem called the BLR test. And the way the BLR test works is very simple. You have a tester which selects 2 points x and y uniformly at random from the domain, and it checks if f of x plus f of y equals f of x plus y holds. So if f is linear, then by definition, this equation always holds. But the important property which makes this tester work is that if f is epsilon far from linear, then the tester rejects, that is, this equation fails to hold with some positive probability delta, which depends on epsilon, but critically does not depend on n, the size of the vector space. So given this tester, you can repeat this test to boost the rejection probability up to, say, 2/3 or something. But the number of queries you need to make to do this test still only depends on epsilon. So in general, in the field of arithmetic property testing, we'll be interested in studying which properties are testable. To be a little bit more precise, I should tell you what testable means and what I mean by a property. So in this talk, when I say testable, I mean testable with constant query complexity and one-sided error by an oblivious tester. I won't precisely define those terms, but you should think of this as just, is there a tester that works sort of like the BLR test, where it does this random subsampling and then determines whether or not the function satisfies the property. And the properties I'm going to be interested in are called linear invariant properties. Now, a linear invariant property is just any property of functions from a finite field vector space to a finite set, where the property doesn't depend on the choice of basis of the vector space. That is, it's preserved by linear automorphisms of the domain. And basically, any reasonable property you think of will be linear invariant, anything like being a linear function, being an affine function, being a low-degree polynomial. And there are lots and lots more examples, even ones which aren't algebraically defined. Basically, the only thing which wouldn't be a linear invariant property is something like being a K-junta, since you need to pick a basis to define what that means. So we won't consider that, but we'll consider basically all other properties. So there's a conjecture in this field, which is that a linear invariant property is testable if and only if it satisfies a combinatorial classification known as being semi-subspace hereditary. This conjecture is from Bhattacharya, Grigorescu, and Shapira in around 2010. So a property is called subspace hereditary if it's preserved by restricting your function to linear subspaces. And this semi-subspace hereditary is a slight technical modification of this that I won't get into. So Bhattacharya, Grigorescu, and Shapira, they prove that the only properties which could be testable are the semi-subspace hereditary properties. And there's been a lot of work over the years on showing that different specific properties are testable. We already saw the example of testing linearity, and I've included on this slide most of the works done that prove that different classes of properties are testable. So let me bring your attention to one work by Bhattacharya, Fisher, Hatami, and Lovet. This is the work, the last work before ours, essentially. They show that a large class of subspace hereditary properties are testable, subject to two restrictions, which we'll get to later. They show that subspace hereditary properties are testable if they satisfy a technical constraint known as bounded complexity, but also they have to be translation invariant for their result to hold, which is means just that if a function satisfies the property and you translate the domain, then the new function satisfies the property. So now to get into our work, we show that all the semi-subspace hereditary properties are testable. That is, we remove these two restrictions present in the previous work. So let me put that on the slide. We show that all semi-subspace hereditary properties are testable, which combined with this only if direction by Bhattacharya, Grigorescu, and Shapira completely classifies the testable linear invariant properties and resolves this conjecture. So in the rest of the talk, I want to explain some of the techniques used in this field and the innovations present in our work, which let us overcome some of the barriers in previous works. So the main technique used in arithmetic property testing, and basically all of the past works I listed on that slide, is what's known as the arithmetic regularity method. And this is conceptually very similar to the graph regularity method, which has had a lot of success in studying graph property testing in the dense graph model. So in broad strokes, the way the arithmetic regularity method works is you have a function f on your finite field vector space that you want to understand. So what you do is you chop up your vector space into nice pieces such that the function you're studying restricted to most or almost all of these pieces behaves nicely. It has to be what's called regular or quasi-random. So the first person who used the arithmetic regularity method was Ben Green in 2005, who had who proved that arithmetic triangle freeness was a testable property. And his proof used a lot of Fourier analysis as the main machinery to make this arithmetic regularity method work. And his technique can be generalized to work for a class of properties which are known as complexity 1, which is a technical definition that I won't be able to define here. But more modern works to go past this complexity 1 restriction to higher complexity properties move beyond Fourier analysis to this field that's now known as higher order Fourier analysis. So there's been a lot of work done over the past decade in developing the tools necessary to make higher order Fourier analysis work. This has been done both by people in additive combinatorics and combinatorial number theory, but a lot of this work has also been done by theoretical computer scientists specifically for this arithmetic property testing problem. So if we go back to this result of Bhattacharya, Fisher, Hatmi, and Lovet, I guess the main summary of their paper is they prove a lot of new strong techniques in higher order Fourier analysis, and combining them all together, this is the best property testing result they can get. They prove the subspace hereditary properties are testable subject to 2 restrictions, what's called the bounded complexity restriction and the translation invariant restriction. So the first new tool in our result is a stronger use of higher order Fourier analysis. We prove a better arithmetic regularity lemma, and that lets us remove this first restriction, bounded complexity restriction. Getting into this is pretty technical, so that's all I'm going to say about this. I want to talk more about the second restriction, the translation invariant restriction, because I think that's much more intuitive what's going on there. So to give a kind of intuitive explanation in why this translation invariant restriction pops up in a lot of previous works, the main idea is the following. If you're studying a general subspace hereditary property, the origin of your vector space plays a special role in the vector space. It's the only point which is fixed by all linear automorphisms of the domain, and that makes it special from the point of view of property testing. But this is unfortunate from the point of view of higher order Fourier analysis because of a counterexample function constructed by Ben Green and Tom Sanders. They construct a class of functions for which higher order Fourier analysis is not capable of regularizing or understanding in a neighborhood of the origin. So this means higher order Fourier analysis is kind of the wrong tool for studying general functions around the origin. So the way a lot of previous works got around this is if you're not considering a general subspace hereditary property, but you only care about translation invariant properties, then all points of your vector space play the same role. And you can just ignore the fact that you can't regularize the small region around the origin. It turns out it won't mess up your property testing result. But to study a general subspace hereditary property, you do need to understand your function around the origin. So what we do to get around this is we introduce a new tool, which is kind of orthogonal to the direction of higher order Fourier analysis. We call this tool patching, and it's a combinatorial technique that's inspired by Ramsey theoretic ideas, and it lets us understand our function or study them on small regions. So we can combine the higher order Fourier analysis, which lets us study our function most places, and then we patch in this little understanding from this combinatorial technique, and combining these two things, you can understand your function on the whole space, which lets us get rid of this restriction present in previous works and solve the conjecture. So that's all I wanted to say. Thank you for listening.
Great, thank you. Any questions? Okay, somehow I think you guys need to be a bit bolder with your questions here, but I'll ask one. So it seems like you've resolved this problem, but what else might these techniques be good for in this property testing area? Like the higher order Fourier techniques and the combinatorial techniques?
That's a good question. So if we look at what happens in maybe graph property testing, we know, which graph properties are testable, but a lot of the work recently has been on more efficient testing on, which properties can be tested in polynomial time or exponential time. And there hasn't been as much corresponding work in arithmetic property testing. So I think that would be a very interesting direction, figuring out which properties can be more efficiently tested.
Any other questions? Again, feel free to also ask questions over chat. Okay, well, thank you again. And next speaker can start setting up.
Okay, thank you.
Can you see the screen?
Yes.
Okay, good. Let's see, full screen. Okay. Should I just go ahead or should I wait till 12:30, 11:30?
Maybe wait one more minute and split the difference.
Sounds good.
Okay, so our next speaker is Raj Jairam from CMU, testing positive semi-definiteness via random submatrices. Go for it.
Thanks, Paul. Yeah, so I'm going to tell you about this this property testing problem, kind of similar to the last talk in some ways in the high level, but for the property of positive semi-definiteness. And yeah, so this is actually a joint work with Ainesh Bakshi, who's also from CMU, and Nadia Shea-Perko, who's at MIT. So I'll start this talk by telling you what a positive semi-definite matrix is, just as a reminder. So we're going to be thinking about square matrices, n by n matrices, in this talk. And such a matrix, an n by n matrix, is said to be PSD, positive semi-definite, if it's symmetric and if all of its eigenvalues are non-negative. So remember, like a standard fact is that if you have a matrix that's real valued and symmetric, then its eigenvalues are also real. So you can order them like this. And then if all of them are positive, I mean non-negative that is, then this matrix is called PSD. And we denote this fact by this little funny notation here, a greater than or equal to 0. That means the A is PSD. So yeah, so like I mentioned, the purpose of this talk is to study this problem of testing whether or not a given matrix is PSD in the property testing model. So in this model, like we're interested in trying to test this property, but without even reading the entire matrix. We want to look at a very small subset, sublinear size subset of the entries of A and determine whether or not it actually is PSD. So that'll be the goal of this talk. And before I formally define this property testing model for this problem, I just want to mention that this this problem of determining in general whether a given input matrix is PSD is an extremely ubiquitous problem in both theoretical and applied computer science. It shows up almost everywhere, and in a lot of places it shows up. So one of the interesting things is that it usually tends to be the bottleneck for whatever you're doing computationally. Like for example, if you have a function and you want to test, let's say it's a differentiable function, twice differentiable, and you want to check if it's locally convex at a point, well, this is equivalent to testing whether the Hessian at that point is a PSD matrix. There's also a very nice property called Schrödinger's criteria that says if you have a finite metric, you can test whether it's embeddable into Euclidean space if and only if a certain matrix is PSD. And there's a number of other applications as well that I won't get into, but the point is that this shows up all over the place, and so understanding when in certain cases we can test very efficiently if a matrix is PSD might be very interesting. So now I want to introduce like the formal model that we'll be considering. So this is the property testing model. So this should feel a little similar in flavor to the last paper, last talk, but what we're looking at is queries to the entries of A. So we're given some matrix A as input, n by n matrix, and we're promised one of two things. Either A satisfies the property that we care about, meaning that A is PSD, or A is epsilon far, I'll get back to that, meaning it's got some gap from the PSD cone. And we want to distinguish between these two cases with, say, constant probability, making as few queries as possible to the entries of A. We want to read very few entries of A. And so the second condition here, I mean, we're saying that either A is contained in this picture here inside of the PSD cone, it is PSD, or there's actually a physical gap between A and the PSD cone under some metric, which I haven't instantiated yet, but which we'll do in a moment. But before I tell you how we're going to measure this distance, I should mention that I completely skipped over this assumption here that I'll now return to. And this is an assumption that we're going to require, and that's that the input matrix that we have has bounded entries. All the entries are in magnitude between -1 and 1. Now I'll mention you can always scale your matrix down so that it satisfies this. So with some senses without loss of generality, but this is going to affect how far you are from the PSD cone. So it won't be entirely without loss of generality. So this model where you're assuming the entries are bounded, this was called the bounded entry model by Balkin, Lee, Woodruff, and Zhang in Soto 19. And the reason it's fairly easy to see that you need a restriction of this form if you want to test a spectral property of a matrix in sublinear queries. And the reason for this is that if you didn't have a boundedness of the entries, I could just take a huge entry like -infinity and hide it somewhere in the matrix randomly. And this is going to mess all the spectral properties of the matrix up. It'll make it not PSD, it'll change the spectral norm and all sorts of things. So I would need to see this entry to determine whether or not whatever a property I'm testing is satisfied. And to do that, then I would need to read the entire matrix because it's just a single entry. So it's easy to see that you need this kind of assumption. Okay, so now I want to return to what this actual distance is. So how are we measuring the distance? Well, it's literally going to be under a metric. So I'm considering the distance from A to the nearest PSD matrix B under some norm. And I'm going to square this norm. It's just for convenience. It makes the statement slightly simpler. Okay, but we're working with matrices. So what are some natural norms we could use? Okay, so the two natural norms we could use that we study in this paper are the spectral norm and the Frobenius norm. So these are going to give rise to two distinct testing problems with two distinct complexities. So in the spectral norm, this is the statement of the spectral norm gap. Either the matrix is PSD or the distance from A to the nearest PSD matrix B under spectral norm is at least epsilon n squared, spectral norm squared. And recall the spectral norm is just the maximum singular value of the matrix. So this gives you a testing problem, but I could also, instead of the spectral norm, I could use the Frobenius norm here. The Frobenius norm is just the sum of squared of entries. This is the same thing as the Euclidean norm if you think of the matrix as a vector. And then the Frobenius norm gap is just going to state that the distance from A to the nearest PSD matrix B is at least epsilon n squared. And now you might ask, okay, what is this epsilon n squared? Why are we saying epsilon n squared? Well, the reason is that, remember, we had this assumption of this bounded entries. This is kind of a normalization. So if all the entries are at most 1, then the furthest you could possibly be from PSD is actually n squared, because the zero matrix is PSD. So you could always move to the zero matrix. So this means that this value epsilon is some value between 0 and 1. And it's measuring how far you are from PSD, with 0 meaning PSD and 1 meaning as far as you could possibly be. And one quick note is that the spectral norm is always less than or equal to the Frobenius norm. This is just a standard fact. But what this means for our case is that if you have this epsilon spectral norm gap, then you also have an epsilon Frobenius norm gap, because the Frobenius norm is always bigger. On the other hand, the converse is not true. The Frobenius norm distance to the PSD cone could be much larger. And this is a great example of that. I won't tell you why this example satisfies this, but it's easy to see that if you have any kind of random matrix, like the entries are independent, then it's not going to have any very large eigenvalues. So what that means is that in squared spectral norm distance, it's only going to be roughly order n far from the PSD cone. But it'll be very far in Frobenius norm. In fact, a constant fraction of its Frobenius mass will be away from the PSD cone, like order n squared. So this is an example where the two differ significantly. And now I want to mention the main results of this paper. And the main results are to understand the query complexity of property testing for these two testing problems. So for the first result, we actually completely characterize the complexity of testing, the number of queries you need for this spectral norm gap. So we give tight upper and lower bounds of theta 1 over epsilon. So this is tight actually up to log 1 over epsilon factors. And these are non-adaptive testers. They don't, similar to the last paper. So for this Frobenius norm gap, it's a little bit harder because, like we said, the Frobenius norm can be larger. So we give an upper bound that makes 1 over epsilon to the 4th queries and tests whether or not you're PSD or epsilon far in Frobenius norm gap. But we don't fully characterize the complexity of this Frobenius norm gap. We do give a lower bound, and the lower bound is only 1 over epsilon to squared. So for this Frobenius gap problem. So this actually separates the complexity of Frobenius gap from the spectral norm gap, because this is strictly larger. But just a quick picture of what our bounds are, we're characterizing the complexity of the spectral norm gap at 1 over epsilon queries, but there is a quadratic gap between the upper and lower bounds for the Frobenius norm, and this is the main open problem that's left by this paper. So these are the main results of the paper. We have some smaller ones as well. But what I want to talk about in the next 2 minutes is just what the algorithm is, because the algorithm is incredibly simple, but it's the analysis which we need to worry about. And the algorithm can just be sort of, you could come up with it once you know this following very simple fact. And this following simple fact is that if you have a PSD matrix A, all of its principal submatrices are also PSD. So a principal submatrix, which we're denoting here by A sub T, that's just any matrix that's a square submatrix where the row indices and the column indices are the same. So if you're PSD, all such principal submatrices are also PSD. Okay, so what's the algorithm? Well, the simple algorithm is, and this is the only algorithm we consider in the paper, although it need not be the only algorithm. The lower bounds hold for any algorithm. So the algorithm is, I'm just going to sample a bunch of these principal submatrices, AT1, AT2, up to ATK. They can have different sizes maybe. And then I'm going to sample them, I'm going to query those submatrices, and I'll check whether or not they're PSD. Now I know if I query one and I see that it's not PSD, I can conclude right away with certainty that the overall matrix was not PSD, because I have this fact up here. So the task is to show that if it's not PSD, you can find a non-PSD submatrix. So because of this fact, this algorithm has this nice property in the testing literature called one-sided error, which means that if it's the input matrix is PSD, I always say PSD, because I'm never going to find a non-principal PSD submatrix. So the main task in the paper is to try to say a converse to the earlier statement. We want to say that if A is actually far from being PSD, then many of its principal submatrices are not PSD. Many of them, in fact, many small ones. So if we sample a random one, there's a good chance we'll find a non-PSD submatrix. So this is the main task of the work, by analyzing sort of the eigenvalues of random submatrices, showing that you can find -1. So I just want to end with the main open problem left by this work, which was that we initiated the study of this Frobenius gap problem, but we didn't close the complexity for the Frobenius gap problem. And one of the reasons is there's some sort of strong barriers to moving beyond 1 over epsilon to the 4th that we discuss at length in the paper, and maybe briefly also in the longer version of the talk if you're interested in those. But I think it would be very interesting to close the query complexity here. And finally, I'll mention that this model of property testing for matrices, there's a number of works, many works studying matrix rank, but there's a number of recent works studying testing of spectral properties like the spectral norm. But one property that has so far been very elusive for understanding query complexity is the Schatten-1 norm. And so far, we don't have any non-trivial algorithms for querying and estimating the Schatten-1 norm of a matrix in the bounded entry model. In particular, as far as I know, the best upper bound is just to read the entire matrix. Whereas there's a number of lower bounds that have been derived already, including a new lower bound in this work, which apply to this property testing bounded entry model. So far, I think it would be really interesting to show maybe whether or not you can get any non-trivial upper bound for estimating things like the Schatten-1 norm. So that's all I wanted to say in this talk, and I encourage you to check out the longer version of the talk if you're interested, or chat with me afterwards. Thank you so much.
Great, thanks. Good talk. So, okay, I see we have a question in chat. Does the 1 over epsilon lower bound for non-adaptive imply a 1 over square root of epsilon lower bound for adaptive? What do you think should be
so actually, so I didn't mention this, but the lower bound for the spectral norm here, so let me just go back to it. This lower bound for the spectral norm gap holds even for adaptive algorithms. So the upper bound is not adaptive, but the lower bound holds for adaptive algorithms. So this is actually tight for adaptive and non-adaptive. On the other hand, the lower bound for the Frobenius norm only holds for non-adaptive algorithms. And the hard instance from this actually breaks if you consider adaptive algorithms. So we understand the non-adaptive and adaptive query complexity of a spectral norm, but we don't understand either for the Frobenius norm. I hope that answered the question.
I was just going to ask a follow-up question. So what kind of adaptive algorithmic techniques might be tempting here?
So that's a good question. I really haven't, after thinking about this for a while, I really haven't thought of any natural algorithm other than the non-adaptive one we mentioned here. Can't see how adaptivity would really help very much, because in some sense you're trying, like, the thing. Okay, so where is this the lower bound for spectral norm comes from the following thing. I can like hide a small fraction of rows with a bunch of negative ones in them, and so that those rows are like giving me a large negative eigenvalue, which is making me far from the PSD cone. And then to figure this out, I'll have to find these hidden entries, like I'm hiding this negative mass somewhere. And so it's just like randomly hidden, and adaptive algorithm is not going to help me find it. I just have to find, it's like, you know, if I keep sampling things, I'm going to see this like zeros until I find the -1. So in some sense, the challenge here is not like additivity versus non-additivity. It's just I have to find something that's hidden in a haystack. For the Frobenius gap problem, I feel like this should be the same thing in some sense. Unfortunately, it's a lot harder to analyze this Frobenius gap problem, because you sort of need to use tools from random matrix theory to understand the eigenvalues of these submatrices. Whereas for the spectral norm, it's kind of more like a needle and haystack type argument. You just want to show that like you can find the negative, the part of the matrix which is negative. So my intuition is that additivity shouldn't really help too much for this problem, but I could be totally wrong.
Any more questions? Okay, I'll just ask one more trivial thing. Schatten norm versus Frobenius norm versus spectral norm. So which one seems most useful to you here? So any perspective on these 3 different options?
So Frobenius norm, for the distance or for estimation?
Just in terms of how to look at these 3 flavors of the problem. Yeah, both.
Oh, okay. So you mean you parameterize the distance to the PSD cone by the Schatten norm?
Yeah.
So I didn't mention this. You mentioned this in the longer talk, but one nice thing is for these 2 gaps, they have all of them have a really nice definition in terms of the eigenvalues of A. So it turns out that this gap in spectral norm is actually equal to the magnitude of the most negative eigenvalue of A, and this gap is also equal to the sum of squares of negative eigenvalues of A. So we actually end up thinking about the latter way of testing rather than this weird how far are you from the PSD cone. So for Schatten norm, I feel like this is sort of maybe one of the easier ways of understanding things, because squares of eigenvalues tend to work well with matrix concentration because it's kind of like the Frobenius norm, whereas Schatten norm, like the sum of eigenvalues behaves very poorly. It doesn't decay at an individual rate when you go to a submatrix. Like the thing is that like for a Frobenius norm, if you go to a submatrix, the sum of squares of negative eigenvalues should decay at a given rate that's proportional to how small the submatrix is. But that's not true of a Schatten norm. Like the rate of decay of how the Schatten norm of a submatrix decays is not the same for different classes of matrices. Like for example, for a random matrix, it'll decay at one rate, and for a rank 1 matrix, it'll decay at another rate. So in some sense, Schatten 1 norm seems much worse behaved. So I feel like maybe it's a harder problem, but I'm not sure if it's the right way of looking at it.
Okay, great. Thanks again.
Thank you.
So next speaker, Vasilios. Oh, you are still muted.
Okay, should I start?
Yes.
Okay, good. This is combinatorial group testing and sparse recovery schemes with near optimal decoding time, joined were with math teacher active. Okay, so let me start with a riddle, which is actually the problem. There are k individuals out of a population of size n. So there are a population of size n, and there are k individuals out of these populations who are infected with the virus. And the goal is to detect who are those individuals using queries of the form. Does a subset S of n contain an infected individual? So for example, if k equals 1, this is a well-known problem. I guess you have seen it in a riddle, or it's like very commonly used in algorithms as a subroutine in some sense, where the jth test, so you make log n tests, and the jth test contains all the individuals whose jth bit in the binary representation is 1. So formally, so using log n tests in k equals 1, you can find who is the infected individual. So formally, you can access a vector x, which is 0, 1 vector of length n, with at most k1s, which are going to be called the defective items. And you want to make m non-adaptive disjunctive tests. So you pick a test S, or many sets S of some size. These are your choice, and you're performing a test, which is the logical lore over all line S of xi. And so if this test is positive, this means that there exists an INS which is defective. And the goal is to recover X with a minimum number of tests. Okay, and here's, for example, an illustration of this. You have some individuals. The first guy is infected or defective, if it's an item. And so the first guy participates in tests 1 and 4. So test 1 and test 4 are going to appear positive, but the other tests are going to appear negative. And the goal is to find that guy from only the outcomes of the tests. And what will be the focus of the talk will be to minimize the time to recover X given the answers. And my focus will be to minimize the time to recover X, trying to be optimal also in the number of tests asymptotically. This problem has many applications. It was introduced by Dorfman in 1943 in the context of testing syphilis-infected soldiers. It has many applications, library screening. I don't know. This is something about COVID-19 testing. This is an image I took from Wikipedia. It's apparently something that someone created during the pandemic. Don't claim it understands or it has any connection to the paper, but you can go to the Wikipedia and see it. I think it's funny. And yeah, and let me now say a bit about the group testing variants, because there are quite many variants appearing in the literature, and sometimes they appear under different guises. So one variant very common is design some tests, let's say a Monte Carlo construction of some tests that allow recovery of all k-sparse vectors, which means that you pick some tests randomly, and then the probability that for all k-sparse X, you can recover X from those tests is at least, let's say, 2/3. Then another variant to design tests such that for all k-sparse X, you can recover a small list containing the support. Now, why this is interesting, one might wonder, and the answer is like, if you allow a small slack, if you allow outputting a small list containing all defective items, but as well some false positives, let's say O of k false positives, then there's almost k, multiplicative k factor gap in the number of tests. And another is to design distribution of a test that you can recover a fixed vector. So that's for every k-sparse X, the probability to recover is at least 2/3. Note the subtle difference where the for all is in the first two bullets, well, it's inside the probability, whereas the third bullet's outside of the probability. So the first bullets are for all you find some tests which work for all vectors, a collection of tests which work for all vectors, while in the third bullet you have a distribution of tests which work for a fixed vector. And the above, you can ask also some error correction, like some tests might give incorrect results, introducing false positives or false negatives. Let's say you have a test which is very common in practice, and it will be also very common in some of the applications we consider. For example, there's a test and there's no one in it, but appears to be positive. There's no actual defective item participating in it, but appears to be positive. Or there are many defective items in it, but appears to be negative. So you have to somehow account for this type of situation. Okay, what this work does, we obtain the correct, and there's an asterisk there, number of tests, which means optimal number of tests, or the best known number of tests, and near optimal decoding time for different variants of the problem, for actually many variants of the problem, including the first three bullets that I have written above, and some error correcting variants. I'm not going to, I'll try to keep the talk a bit high level. And as well as we use all these new tools to get new results on heavy hitters in the strict style model. Like actually we saw that a variant of count mean sketch, which I guess all you know, gives can do more new tricks that weren't known before. We give a new linear sketch that greatly improves on previous linear sketches for compressed sensing. We give an explicit test of construction of tests for group testing, so on and so forth. Like I'm not going, because I guess there's not enough time, I'm not going to talk about all the variants, or I'm not going to define things super formally. But the goal of this work is to take the correct number of tests and be order optimal in recovery time or decoding time. Phrase as you wish. Okay, now let me start with something simple. What's the archetypal kind of framework for all those problems, including heavy hitters, compressed sensing, group testing? You pick R has functions, capital R, which has the universe down to k buckets. And then for each bucket and for each hash function, you perform a test, let's say. Which means that all the i's, which are hashed to the bth bucket under the jth hash function, belong to the same test. So you have O of k times R tests. Okay, and I think this sounds very standard, and that's true. So and now how should you recover your vector? How should you decode in such a situation? You iterate over overall coordinates and check if it belongs to a negative test. That's it. And this will be called a naive decoder. The interesting thing now is that if you start adjusting the value of R and playing a bit with analysis, this yields all different Monte Carlo constructions, like for group testing. There's an asterisk there. There's one that does not follow from this framework. It uses Reed-Solomon codes, but let me assume that this is all. And interestingly, it's not particularly hard to observe that if you substitute the OR operator with plus, let's say you, instead of working over true false, you work over, I don't know, the real numbers. This is exactly the count mean sketch, actually. Actually, it's a variant of the count mean sketch. For R equals log n, you get the count mean sketch. So it's not particularly hard to see that all those hashing type, all those problems can be put under the same hashing type framework. Okay, but now what happens to sublinear decoding? There was a long line of previous work. I'm not going to talk about it. It's mostly based on something called least recoverable codes and all the jazz, which come with big constants that are quite complicated. What we show here, we show that look for many variants of the group testing problem and some variants of the heavy hitters problem and compressed sensing. You can bypass these least recoverable codes and get much stronger results and without all this machinery, using only elementary methods. And our goal is again to be test optimal or space optimal if we're in heavy hitters, or row optimal if we're in compressed sensing, and still achieve near optimal recovery time up to log factors. and also try to avoid as much as we can the least recovery. Well, we almost avoided that. For one of the variants we consider, we unfortunately still have to invoke some of this least recoverable jazz. And this is the preliminary theorem. So this is a starting point of our paper, which can then be used. It's like one of the main building blocks is the following. There exists a Monte Carlo construction of k log n over k tests, which allow the following property. Given the answers to the tests, you can find in O of m time, like in O of k log n over k time, a small list which contains all the defective items. This is starting. This is the building block and the starting point in our work. And this is kind of performs universe reduction. The idea is very simple. And after that, things are kind of start becoming more simple, because after getting L, you just run the naive decoder, the naive recovery algorithm only for elements in L. It means that you go over all elements in L and just ask, does I in L belong to a negative test? If it belongs, then I throw it away. I'm not sure I have time how to prove this preliminary theorem, although it's pretty short. The proof is just 1.5 pages apparently. You can add then some error correction to the above, and then apply some new and old tricks to obtain all the results for heavy hitters and all the results in the papers. Then you can extend to comprehension using an ad hoc argument. But the whole, let's say, the bottom line of this work is that there exists O of k log n over k tests, which allows you to find rapidly a small list of size O of k log n over k that contains all the defective items. And this list is then small enough so that you can iterate over it. How many minutes do we have left? Do I have 1 minute?
Sure. We may not have time for questions, but yeah.
Oh, yeah, it's fine. Questions then. Okay, that's the bottom line. Then some math. Yeah. And yeah, I guess the proof is actually simple. It's like it's significantly simpler than the least recoverable code's machinery, like established the previous work, and it gives much stronger results. And I hope there are many new algorithms and consequences that we haven't discovered yet. Yeah, go on, please. Thank you.
Okay, thanks. Yeah. So, any questions about this?
Where is the explicitness coming from?
Oh, sorry, I didn't hear you.
Can you say a little bit about the explicitness part of the construction?
Okay, the explicitness. Wait. Yeah. Okay, the explicitness actually is, yeah, how to say it? Let me think, what's a quick answer for this? I guess the idea is, I don't know how to say it without being too technical. Okay, the idea is that we have explicit constructions only for a disjunct matrix. We have an explicit construction of an efficiently decodable disjunct matrix. And what we do is we construct a highly suboptimal least disjunct matrix, the number of rows of which is still within the allowable number of rows of a disjunct matrix. Yeah. So we're able to turn this by paying a factor of k more, a multiplicative factor of k. We turn this construction by paying an additional multiplicative factor of k into a deterministic construction, which is terrible for least disjunct matrices. But I don't know if you know what least disjunct matrices are, or I'm just talking nonsense. Yeah, I mean, it's kind of hard to tell how you do this, let's say, in 1 minute. But I can tell you offline, like if you wish. I can spell all the details offline. Like
yeah, thanks.
Okay, thanks. So time for our next and last speaker.
Let me unshare.
Yeah, again. So. Right. Okay. Can you see my screen?
It's black at the moment.
It's black.
Oh, okay. Yep.
Oh, I can do it. Yeah, like this. Should I start?
Yes, please.
Great. So hi everyone, I'm Evangelia, and this paper is about Pandora's box with correlations. This is joint work with Suchi Zhao, Yifeng Teng, Christo Zamos, and Rumin Zhang. So I'm going to start by describing our problem a little bit. So imagine that you want to buy your friend a present, like a Christmas present, and you can't really go out of your house right now and go to the shops and buy something. So you know that this specific item you want is sold in a bunch of online websites. So you know some of them might be, they usually have cheaper stuff, or they have more expensive stuff, or they might have some sales or something. So you have some like prior information of on every website, and you don't really want to go search everything over because there are too many and you don't have that much time. So essentially you're gonna go search some of them, and then maybe you decide at some point that, you know, the price I found so far, it's cheap enough for me, I'm gonna buy it from here and not search anymore. So let's make it a little more more formal. So let's say we have n different boxes. These are our n alternatives, and each box has some price inside. We don't know the price, but we have some prior information, which is basically a distribution on this price. So these here are the distributions. So we have some stochastic information on the prices, and we wanna, in order to find out the exact price, we have to pay something. So information is not free, basically. This is the time we spend searching, basically. So this example, in order like to find out what's inside box A, box 1, I need to pay 1. So the red ones are the costs. I need to pay 1, and then I open the box and I see that there's 42 inside. So what I described before and what we're gonna do basically is, what we want to do is open a couple of boxes in some order, and at some point we're gonna decide to stop. This is our stopping rule. And we're gonna say, you know, I'm gonna keep the best price I have seen so far out of the ones I opened, and then I'm gonna stop and not search anymore. So the instantiation of these prices is called the scenario, and we're gonna use that in a while. So this problem comes into two flavors, basically. So in the maximization version, imagine that the boxes have inside some reward. So we want it to be high. So in that case, we want to maximize the maximum price we find so far, or the maximum reward, minus whatever we paid in order to find that out. So the information cost. In the minimization version, on the other hand, it's basically the example I described with the present. So we want to find the cheapest option, and we want to minimize the minimum price we found so far, plus whatever we paid in order to find that out. So in this paper, we're going to focus on the minimization version. We have a smaller result on maximization. I'm going to talk about it towards the end. So let's see first what's been done so far, what do we know. This problem is basically Pandora's box, which was first described by Weizmann in '79. And it turns out that there is a very simple and elegant greedy strategy that gives the optimal. And what is the strategy? So we're going to assign an index to every box. This is called the reservation value. And we're gonna order these boxes, the boxes based on this index, and we're gonna open them in that order, right? So as we keep opening, we get a new lower price, a new better price until now. So whenever our current best price is better than the index of the next box, we're gonna stop. And this gives the optimal. This simple strategy gives the optimal. But there's a crucial assumption in that case that the distributions are independent. So what we asked in that paper is basically what about correlation? So what happens if we're given sample access to some arbitrarily correlated distribution? So we don't assume anything about like the type of correlation these distributions have. So it's worth noting here that the related problem is optimal decision tree, but usually they require either small support or explicit distributions, so it doesn't really fit in our setting. So let's try to solve it. Let's see what can we do to approximate the optimal or find the optimal. Consider the following hard example. So let's say we have these boxes, and we need, so the location of the best box, the cheapest box in that case, is encoded somehow in the prices of the other boxes. So we need to, maybe in this example, we need to open box I and box J. We're gonna see that inside they have values 4 and 2. And now we know that we should go to box 42 and get the minimum price, which we know it's there. So the problem here is that we cannot learn that's an arbitrary mapping, and we can't learn it with finitely many samples. But okay, let's back up a bit now. So the strategy I described is like looking at whatever we found inside the boxes and then adapting what the next box will be. So is that the only possible strategy? What other strategies can we think about? And let me describe a bit more detail what is a strategy. A strategy is basically an algorithm that has two components. So this algorithm, the strategy, tells us what at every step tells us what is the next box that we should open and when should we stop. So two components. What I described so far is basically what we call the fully adaptive strategy. And this says that both the next box and the stopping time, where we stop, are both adaptive. So adaptive means that they depend on the values we've seen so far from the boxes we've already opened. Okay. On the other end, the non-adaptive strategy, the order is fixed and the stopping time are fixed. So fixed order and stopping time, I mean that basically we choose we fix a set of boxes and when to stop, and we open them all at once. Okay, so this has nothing to do with the values that we see inside the boxes. So in between these two, there is another strategy, another family of strategies we call partially adaptive. And in that case, we fix the order and we will open the boxes only in that order, but the stopping time can depend on the value we've seen so far. And the nice thing about this strategy is that it's not like something we just thought of and defined. The algorithm I described before, called the Weizmann algorithm, is basically a partially adaptive strategy. So this family of strategies give the optimal for independent distributions. So let's go back to our initial question. What can we approximate now with all these strategies? So the fully adaptive, we said that this is hard to do. So what about non-adaptive? Again, in that case, things do not seem very hopeful. So both learning and approximation is hard. And for the learning part, think that there exists some tiny probability scenario that has price infinity on every box except for one. So in order to avoid infinite expected cost, we need to query all the boxes or sample this tiny probability scenario. In terms of approximation, again, think that the boxes only have 0 and infinity prices. So in order, again, we need to find a 0 for every scenario, basically, so that we avoid infinite cost. So this is basically the heating set formulation of set cover. So again, this seems to be hard to approximate. So what we showed in this paper is basically that we can efficiently learn and approximate this family of partially adaptive strategies, which are, remember, between the fully adaptive and the non-adaptive. And our main theorem says exactly that using polynomially in n is the number of boxes. So polynomially in the number of boxes sample scenarios, we can efficiently find a partially adaptive strategy that is constant competitive against the optimal partially adaptive. And so this is a summary of our results. So our main result, it's this constant approximation for partially adaptive. And this is basically, we do this using a reduction to the mean sum set cover problem. Then we also saw the lower bound in that case, again, a constant lower bound. And we also explored a couple more variants. So what happens if we have a different feasibility constraint? So let's say we want to choose k items instead of 1, or we want to choose a matroid basis of rank k. And in these cases, we saw the constant approximation and the log k approximation. And for the matroid case, we also saw a matching lower bound. And these two results are based on the generalized version of mean sum set cover. And their algorithm is actually very similar. So a smaller result for the maximization version of the problem. Everything I said so far is for the minimization. For the maximization, we saw that we cannot approximate the non-adaptive using a fully adaptive within any constant. But it's not clear. This is open. It's not clear what can we approximate. So basically, our work shows this trade-off of adaptivity versus computational complexity, and a couple of future directions would be like a couple of open questions would be: what can we approximate with fully adaptive strategies, and if we can actually use these adaptive algorithms for more general and maybe harder combinatorial problems. And that's all. Thank you very much. If you have any questions, I'd be happy to answer.
Great, thank you. So yeah, I'll start off with one question. So could you tell us a little bit about the kind of modeling? So in terms of, I don't exactly know how this relates to practical scenarios, but so you're looking at all possible high-dimensional distributions of these valuations, but then a rather restricted class of algorithms. Is it, are there other blends of these assumptions that might also work? So like a more restricted class of distributions, but a more general class of algorithms?
More restricted class. We haven't looked into more. You mean like assume some type of correlation, some specific type of correlation or something like that?
Yeah, this is so just the worst case instance you presented early on with this 42, this kind of index function
Right.
is a really scary kind of setting. But if you showed it to an economist, they'd probably say this is an unrealistic setting in real life auctions or things like that. So is there some kind of more restricted model which might allow for stronger algorithmic results?
Maybe we haven't looked into that. Yeah, I'm not sure actually. Yeah.
So if I may add something. So actually the optimal decision tree line of work does pretty much that. They assume that the distribution is small support, so it's a support M distribution, and then it optimizes. So optimal decision tree you can think of as a special case of this problem we're looking at, but then this work optimizes over the class of all fully adaptive strategies and gets approximation factors that depend on this support size. So that's one example, but yeah, there's a whole spectrum of what one might be able to do.
Okay, yeah, thanks. That answers my question. So we just got another question in chat from Alec Johnson. Have you looked at specific applications of this problem for really small n, like n equals 2? In this case, maybe you can get exact solutions that compare across the hierarchy from non-adaptive to fully adaptive.
Okay, no, we haven't looked into something for small n. No. Small n. But usually, so the whole point is to like minimize the time you search. So if you just have two boxes, then I mean, just go ahead and search all of them. Right. I mean, the whole point is to not search everything. If you can search everything, I'm not sure if that even makes sense. Does that answer your question?
Kind of. You might consider a difference between n equals 1, like searching n equals 1 and n equals 2. But also there's cardinal information costs on the boxes, aren't there? So you might have a significant interest in only looking at one of them. I don't know. Also, part of it is just the question of tractability, like what do optimal solutions look like for a really.
Sorry, I missed the last part.
Sorry, for what do optimal solutions look like for really small examples? That's just kind of the flavor of the question, but if you haven't looked at it, then it's going to be hard for you to answer.
Yeah, we haven't really looked at it. Yeah. Yeah.
Oh, and okay, so I guess we just got another question in chat, which related to what Shuchi was saying earlier. So other class of distributions that might be worth studying, those with coordinate permutation symmetry. I'm just reading from chat to try to get a discussion.
Yeah, we haven't looked into any like specific distributions. Like we didn't want to assume anything. It's like the most general thing. Yeah, maybe something more specific would also make sense. I don't know, but we haven't looked into that yet.
Okay, great. Well, thanks. So if I could just ask everyone briefly to unmute themselves, just to thank all the speakers with a brief round of applause.